So I'm happy that everybody's still here. I was a little bit worried at the end of the day that things would start thinning out. So hopefully I don't let anyone down. But so my name is Christian Peron. I work for a company called Fastly. We operate a content delivery network, which means we got a lot of infrastructure deployed globally, a lot of systems that need security, obviously, take it pretty seriously. So I'm on the security team. I kind of have three main areas of focus: architecture, making stuff that we're building secure, and hopefully not having to add security after the fact. So we're pretty good about that. Security research. I spent the last couple of years primarily focused on the security research team, where we were kind of prototyping threat identification and containment technologies. And then finally, operations. So I'm also on the triage rotation, which means that I'm dealing with our intrusion detection alerts, vulnerability reports that are coming in, and that sort of thing. So I'm involved also kind of like operationally on the team, which gives me pretty good, I guess, exposure to some of the problems that you run into when you're trying to do security on a large environment. So what I want to talk about today is basically talk about some R&D that we've been doing around security telemetry. We'll talk about what that means and why people should care about it. Some different sources for telemetry and different subsystems that you could use to basically extract information to look for indicators of compromise or IOCs. Take a look at the prototype that we built. So it's kind of two parts. We're leveraging an open source project built by another company doing pretty cool stuff, and then there is like basically the integration of that technology into our environment and how we use it to basically collect telemetry without destroying the performance in our environment, which is also really important for us. And then just kind of conclusions and wrap up. So telemetry, I know it's kind of an overloaded term in the mechanical engineering world and chemical engineering world. It has very very specific meanings. But the one that kind of more resonated with me was one of the definitions off of Wikipedia, which kind of defines telemetry as an automated communications process by which measurements and data are collected from mostly inaccessible systems. The data will come back to a centralized area for an analysis. The data could contain either metrics or data or other things. It could be like pressure sensors or whatever the case may be in kind of like the SCADA and mechanical world. But for me, it's a little bit more simple than that. When I think about security telemetry, we have a lot of devices in our environments. We got switches, we got firewalls, we got servers. All of these things are producing a huge amount of data, oftentimes which could contain indications of compromise. But so it's a matter of being able to collect that information, ship it in a scalable format, and basically have the technology in place to identify when we think something is being compromised. So some of the high-level requirements and why we need it. Anybody who's responsible for security in any kind of an operational environment knows that you want to have data in place to assist with investigations, to assist with forensics if you suspect that something has gone wrong in the environment. And oftentimes you shouldn't have just one intrusion detection function in the environment. So it's very common that you might have like host-based intrusion detection, antivirus, network-based intrusion detection, and all these things are kind of telling you when something might be going wrong in the environment. And then basically it's up to the security analyst to log in and try to make sense of why are we seeing these alerts or these false positives or these things that we need to be concerned about. So I think using that telemetry to correlate stuff from an intrusion detection process, both host and network-based intrusion detection, is really important. The other area I think is actually really important is less to do with malicious attacks, but if you operate networks where there's a wide range of users that are logging into systems, performing actions on those systems, they may not be doing something intentionally wrong, but they could still be executing stuff that exposes the environment to additional risk. So you want to be able to identify when this is happening. So this could be something as simple as like an audit trail of what's being executed on the system. But I guess like the bottom line is that we want to know who did what and when, and we want to be able to answer those questions hopefully in a non-evadable and a performant manner. And we'll talk about kind of the importance, at least for us, and when it comes to performance, being able to do this. So I just want to draw out a couple like tangible examples. So a lot of us who have network-based intrusion detections and network-based intrusion detection sensors, rather, it's pretty common. You'll see like alerts when there's suspected communications with either known command and control systems out on the internet or just known bad actors. Usually there's a blacklist, you know, and so on. And when we're seeing inbound communications from these bad actors, it could be concerning, especially say if it's coming to a port that shouldn't be running on that host. So immediately there's a few questions that we want to answer. Is this service actually listening? So if I have like a web server and I'm seeing inbound communications to like port 8080 or some other service, is that service actually running on the system? And if it's running on the system, did it actually accept the connection? If the machine was compromised, on the other hand, there could be like a rootkit or an implant installed on the node that's basically, that will hide sockets, that will hide processes, hide the presence of kernel modules and that sort of thing. So it becomes kind of not really a guessing game, but it becomes more difficult in terms of like trying to determine whether or not a system has been compromised. The other thing too is like in many cases, depending on the source of like your NetFlow data, a connection may not necessarily have needed to be accepted or established in order for NetFlow records to actually be created. So in some cases, if there's network access control in place, there may have been an attempt to communicate, but let's just say the ACL has dropped it, but because of how certain NetFlow generators work, they'll end up generating flow records for that connection anyways, which muddies the water. So in this case, having a record of which kernel modules have been loaded, which connections have been accepted, anytime we've bound sockets to listen onto the network, you know, any kind of outbound communications would be, having an audit trail of that stuff would be really valuable for us, and especially if we have it in a way that we're shipping it off the system so that we're moving it to like a trustworthy location. Another example that I point out is, this is kind of more of like a host-based intrusion detection correlation where we're seeing, you know, it might have been invalid protocol negotiations on SSH between two internal systems. And so immediately we want to know like what, so these are systems that, you know, we might own. What was running on these systems at the time this happened, and more specifically, who is actually responsible for these? Because this could indicate that if a system was compromised and it's trying to scan within the internal environment, it could be an indication of lateral movement within a network. And so we need to know, like, basically what was running, who is running on, who's on the system, what users were those processes running as, that sort of thing. So, and the other thing is, we kind of get this. If you're in an environment that's using like sudo as an example, anytime that there's a command that requires privilege, there'll be an audit trail that gets created. I don't want to use the term audit trail. There'll be a log that gets created. It's probably a better way to put it. And, but in some cases, if you think about like a Bitcoin miner, or you think about certain other utilities on the system that may not require privilege, if you're not using things like sudo, if things like sudo aren't required to execute these utilities, and you're going to be basically completely blind, and these utilities could still actually represent risk to the system. So where do we get this data? This is not a unique problem to us. We have kind of unique requirements in terms of how much volume, in terms of accepting connections and initiating connections during origin pull from the fleet and that sort of thing. So this isn't not a problem that is necessarily unique to us. So the most common source for this data usually comes from security event auditing. And in Linux, it's typically known as like Audit D. So Audit D is kind of the user space implementation of a security event auditing framework. When this framework was designed, it was designed to basically be evaluated against common criteria and meet things like CAP, as an example. And there's a lot of really stringent requirements associated with common criteria. So a couple examples that I tend to give is there needs to be an upper bound on the number of audit records that you can lose in the event of an unexpected power failure. So when you think about it, it doesn't really seem like that intrusive of a requirement, but what that basically means is that you need to throttle how many in-flight system calls can be running at the same time. So if you need, let's just say you want to say 128, at maximum 128, then you can have no more than 128 system calls in flight. And when we're looking on a cache, like we have thousands of operations that are in flight, and we don't want to be throttling that to meet this CAP requirement. Another example is if an auditable event is selected to be audited and it cannot be audited, then the event cannot happen. So if you think about things like a transient memory failure or memory allocation failure that results in us not being able to allocate the data necessary to create the audit record, usually what would happen is that operation would fail, but we wouldn't necessarily want to fail the connect operation from occurring, as an example. But based on CAP, we have to pre-allocate all that stuff ahead of time and basically ensure that there's no, typically what we would consider like a transient failure that is going to be able to impact our ability to execute this operation. So in general, I think that these are really good requirements because what they've done is they've made the audit trail very reliable. They've made it, there's high integrity requirements, which is something that is really important when you're thinking about an audit trail and you're using this to kind of inform security decisions. But these also have a very negative impact on performance, which we'll go into in a little bit. Certain other operating systems, so I personally, I worked a little bit on the Mac OS and FreeBSD auditing framework. Things are a little bit different there. You can have you can have per process audit configurations, but there's still kind of these same requirements in terms of like robustness and pre-allocation. The other thing too is that the number of the types of events that are auditable are fairly static, which means that we have these system calls that we consider to be security irrelevant, and these are the system calls that you're able to look at. So if there's certain other operations or functions that are security relevant in the context of a specific exploit, you're not necessarily going to have the system create an audit trail for you, and we'll talk about why that's important. Right. So, right, and again, and when we talk about like on a cache where we have like thousands of connect operations potentially happening at once, we don't want to be like slowing that down. So these are some performance numbers from a few different sources. So Linux Foundation, Red Hat, IBM. So the first stat is that when they disabled audit on SE Linux enabled system call, they went from 75 down to 41 nanoseconds, which is a pretty substantial performance penalty. In other cases, having the call audit entry and audit exit resulted in some 20% performance penalty. And then in certain other cases, it's a difference between going from 200,000 operations per second down to 3,000. Now, some of these performance metrics, they're old, and these may have been improved in kind of more modern versions of the kernel, but there's still kind of other issues outside of performance. And I don't think that the other one that I brought up is that what you end up having is like a monolithic audit configuration. So you can't say, I want to audit these operations for this collection of process and those operations for that collection of process. You're basically stuck with one global configuration, which could be problematic, especially for us. So the other thing that I kind of alluded to is exploit mitigation bypass operations. So the other thing is you want to be able, if there's an exploit that is starting to run on a process, you want to know immediately, especially if you're in a situation where you want to have like an attack disruption function where if you see the beginnings of an exploit starting to unfold, maybe you want to detonate the container or kill the process or whatever and take options. And you want to do that preferably while the exploit is basically starting to get going. So there's a lot of exploit mitigation mechanisms out there. So some of the most kind of like common ones were things like DEP in Microsoft, or just like the non-exec stacks in a lot of operating systems, which basically prevent an attacker from uploading the code associated with like let's say shellcode payload and having that execute on the stack. Things like WXRX, which basically required that you can't have like a page of memory that is marked as executable and writable at the same time. So there's all these kind of exploit mitigations. But for every exploit mitigation, people figured out ways to get around them. So really popular mechanism to get around like things like non-exec stacks are rob chains and things like stack pivoting, which basically allows the attacker to construct stack frames, not actually include the code, but actually leverage the executable code that's already mapped into the process. And we want to be able to see. So in order to do this, the attacker needs to basically have control over a region of memory. And depending on the exploit, there may be a series of either like stack, we're rebasing stack pointers, or we're using other memory protection operations to set up the pages so that we can actually run our exploits. And so these are generally system calls that we wouldn't consider to be security relevant. We may, depending on the operating system, you may or may not be able to even produce an audit record for them. Another case like SMEP and SMAP. So these were controls that were implemented to prevent user space from accessing memory in the kernel and prevent user space from executing code that basically resides in the kernel. So in some cases where the kernel is the attack surface, you may see the exploit start off in the kernel and disable these functionalities so the remainder of the exploit can actually operate within user space, which makes it a little bit easier to write. So in all these cases, as mentioned, they kind of manifest themselves as like, either memory or stack initialization operations. And we don't necessarily want to have, even if we could audit them, there's some performance implications in terms of doing this in systems. How am I doing for time? So to make matters worse, so I gotta get going a little bit. So to make matters worse, if you look at some of the more recent attacks, like some of the speculative attack or speculative execution attacks like Meltdown and Spectre, there is no real system call really per se. So Meltdown is detectable by hooking the kernel functions that are responsible for handling faults and for seg faults as an example. And then you want to look at the address associated with that fault. And if it's above a certain range and it's in user space, it could be an indication that Meltdown was being exploited. For Spectre, there's also PMC, like performance monitor counters in the processors that kind of will measure things like data cache misses as an example. And if you're seeing this happen consistently and you're able to track those counters, and there could be ways that you can identify that. So what do we do? We can't really, so audit has posed some challenges for us. There's got to be alternatives. So we could write a bunch of kernel modules to hook operations that we are interested. And so we kind of did this with some K-probes. The problem with this mechanism, we still needed a way to get the data from the kernel into user space, which required some sort of serialization. We also needed a way to have kind of like configuration in terms of like, having more control. We don't necessarily want to see exact operations for everything. Maybe we want to ignore certain binaries, which means that there is some kind of configuration interface that was required. So the other areas where we can get this data are dynamic tracing systems. So I mentioned K-probes, K-rep probes, and Linux U-probes, which is kind of the same thing within user space that allows you to arbitrarily hook operations in the kernel and monitor when they're being executed. Different, like on BSD, Mac OS, Solaris, there's things like dtrace, which kind of is similar but has kind of domain-specific language. More modern versions of the kernel have eBPF, which allows you to basically run code at trace points, but the code goes through like a validation process to make sure that it's a little bit safer than something like a K-probe. And then there's like the perf event interface, which is more common. Okay, so what we decided not to do this, and we decided to use something called Capsulate, which is an open source project, and it's written in Go. It's a daemon that allows you to submit subscription objects. It takes those objects, translates them into trace points in the kernel, and waits for certain operations to execute, and then basically will provide a protobuf back to you, back to a monitoring process, which is really cool. So again, it uses gRPC interface, subscription data specified using protobufs, and resulting telemetry that comes back is it also basically it comes back in protobuf format. It leverages the perf event interface to accomplish this, which is one of those dynamic kind of tracing and debugging frameworks. So the architecture, there's basically three main areas. There's the telemetry service, which has an API that you interface with. There's kind of like an enrichment layer, which monitors when processes are being created and that sort of thing, looks up user IDs, looks up credentials, and then the interface, which basically feeds and inserts the probes into the kernel. There's some talk about implementing things in eBPF, but it was mainly using perf event for basically compatibility reasons. So I won't go into that just because I don't have a whole bunch of time. So basically when this happens, you get records that gives you like command line arguments, what was executed, the credentials, timestamps, and that sort of thing. So this is kind of exactly what we want. And it does this, because it's using the perf event interface, we don't have the same performance penalty that we would if we were using audit. This also required that we had to write a component which basically integrates this system into our environment. We're storing the subscription data in JSON, filters kind of stored in an AST format in our configuration management system. It's basically there to suppress duplicate messages, manage the subscriptions, and bind the subscriptions to different control groups. So the interesting thing with perf is that you can have multiple control groups and bind different subscription policies, which allows us to basically say for our edge daemons, we don't want to see things like accept or connect, but we want to see accept and connect for interactive users. So by the use of control groups, this basically allows us to accomplish that. Okay, I got 1 minute left, so I won't talk about this. Basically, this is a service that allows you to move processes in between different control groups on a system. It's called CG Rules NGD. And this is how we're kind of managing things. So conclusions. So dynamic tracing frameworks actually provide you with a really rich set of information that allows you to hook arbitrary operations within the kernel to identify attacks. Evasions are a concern because it's not as kind of robust, so to speak, as security event auditing, which means if you're going to use these, then you need smokescreen detection in place. So to identify situations where people are trying to overload the systems to result in loss, to basically confuse things, and logging volume. And I think that's actually it. I don't know if I have time for questions. It's up to the organizers, but no. Well, if anybody has questions, feel free to come talk to me afterwards. So, all right.